Hey audience, in the last couple of videos I talked about a couple of Napier's sort of mechanical or physical computation tools that help us do multiplication faster. And in this video I want to start talking about one more way that Napier published to do multiplication faster. This is going to be part 1 of 2 to keep the videos a bit more manageable, and in this part I'll talk about how we can do addition faster. Let's back up a bit and talk about how we got where we're at so far. At each step of the way, we've been offloading more and more of our mental work onto physical things. And with the prompt array, we're at the point where we have to do no mental multiplication, no memorization, no writing or copying values. All we had to do was lay out some paper strips and add along the diagonals. But we still had to add numbers. It's not as bad as multiplication, but we still don't want to do it. So how can we sort of mechanize the process of doing addition? In other words, how can we offload the addition to something physical so that we don't have to think about it? One way to do this is to use an abacus. Here's one about myself. I'm pretty proud of it. You'll see some historical sets of Napier's bones often came with an abacus for exactly this reason. If the bones are going to leave you with addition that you still have to do, you might as well bundle them with a way of doing the addition more quickly. The abacus is an interesting tool all on its own, but that's for another video. In this video, I want to talk about a different way of offloading addition out of your brain and onto the physical world. This is Napier's location arithmetic, or local arithmetic, or at least part of it. I don't know how Napier came up with it, or how he came up with anything really, but I want to continue the format I've been using for the last couple of videos of showing how you might have come up with it yourself. So let's say you want to keep track of things as they accumulate. Let's say you have 3 sheep. You could keep 1 token for each sheep in a pile. It doesn't matter what it is. It could be coins, checker pieces,
very small rocks,
whatever you want. Then when you buy 2 more sheep, you can add 2 more tokens to your pile. So 3 plus 2, now you have 1, 2, 3, 4, 5. Now you have something external, the pile of tokens, remembering the number for you, and also doing the addition for you. Nice, we're done. But once you have large numbers of things, your pile of tokens also gets large, and it takes too long to count. You'd like some way to condense this pile a bit. So let's do the same thing we do with our written out numbers. When we write out numbers, we have a ones place, a tens place, a hundreds place. Let's make multiple piles instead of just one. A token in the first pile represents a thing. A token in the second pile represents 10 things, and so on. So now if we have 15 things, we can have piles of 1 and 5, 15. And if we want to add 29 things, we take piles of 2 and 9 and just merge the piles. We can add these up as they are to get our answer, 3 tens and then add 14 ones, so 44 total. But to make the piles even more manageable and easier to read out, we could count up a group of 10 from the ones pile, remove them, and add 1 to the tens pile to represent them. Then we get the same number, 44, but with fewer tokens to deal with and it's easier to read out. So this is better, but we still have to count to 10, and counting to 10 is kind of hard. Maybe we can do the same thing, but with smaller groups like 5. So tokens in the first pile represent things, and tokens in the second pile represent groups of 5 things, and then tokens in the next pile represent 5 of those groups, or 5 fives, or 25 things. And as a side note, this abacus also sort of works in groups of 5, but we'll talk about that later. Counting out a group of 5 is way easier than counting out a group of 10, but it's still kind of hard. So how far can we push this? Well, the smallest group of multiple tokens that we could possibly make is just 2 tokens. So let's break it down into piles that represent 1 thing, 2 things, 4 things, 8 things, and so on. Whenever we have a pile with at least 2 tokens in it, we can remove 2 tokens and put 1 token in the next pile. So 2 ones is 1 2, 2 twos is 1 4, 2 fours is 1 8. So let's try this out. Let's add 5 and 3. First we need to take our numbers and turn them into token piles. 5 is 4 plus 1, so we'll put a token in the 4s pile and a token in the 1s pile. 3 is 2 plus 1, so we'll put a token in the 2s pile and a token in the 1s pile. Then we merge the piles. We could read our answer out just like this if we wanted to. 1 4, 1 2, 2 ones, that's 8. But that's even more adding than we had to begin with. But we could use our grouping rule. These 2 tokens condense into 1 in the next bucket, and then we do it again, and then we do it again, and now we have the same answer, 8, but with fewer tokens to deal with. We also didn't have to break down our original numbers into these sort of doubles if we didn't want to. We could have added a pile of 5 tokens and a pile of 3 tokens into the ones pile, and then condensed them out to the same answer. The real power here comes from the fact that applying this rule of combining 2 tokens into 1 will always reduce the number of tokens that you're dealing with, which should hopefully reduce the amount of actual addition that you have to do at the end when you reconstruct your actual answer. And to assist in breaking down our input numbers, we can also use every Renaissance mathematician's favorite computational aid, tables. Napier also published some tables that let you break down your number into these piles 1 digit at a time, which could be a real time saver. We could take the number 135, for instance, and look up 1 and times 100 and put tokens in those spots, then 3 and times 10 and put tokens in those spots, then 5 and times 1 and put tokens in those spots, then simplify it by pairing the tokens. Now we don't even have to do any arithmetic like subtraction or division to convert our numbers into these token piles. Napier wrote that doing computation like this felt more like playing a game than doing work. And it really does feel more like playing a game like Mancala or something, where we have a rule that says we can take a pair of tokens and replace them with 1 in the next pile. Napier called this abbreviating. We can also do it in reverse, which Napier called extending. Since the moves in this game don't change the value that's being represented, they're totally optional, and it also doesn't matter what order we do these moves in. We always end up with the same answer. An interesting consequence of this rule is that every number can be broken down into piles of either no tokens or 1 token. You've probably already been typing out your comment about how this whole thing is actually just the binary number system, and you'd be correct. It's definitely true that it can be thought of in that way. But that's not the only way you can think of it, and I actually kind of want to discourage you from thinking of this as binary. For one thing, Napier came up with this before the binary number system was really formalized in the way that we use it now. Also, we don't have to reduce everything to piles of 0 or 1 tokens. We can still have piles with multiple tokens. Napier called these abbreviated and extended forms of a number. But the most important reason why I don't want to think of this as binary really has to do with why it feels like a game instead of feeling like arithmetic. But I'll save that rant for the next video.
Alright, so let's see what it looks like if we use the location arithmetic to do all of the adding during a multiplication. So here we have our prompt array set up to multiply 324 by 87. You might not be able to see these numbers too well, but that's not really all that important. And so I have all of my bins down here, and I have a table to convert decimal numbers into these bins. So let's start running down these diagonals. This first diagonal here is the ones. So we have 8 ones, and that's just an 8 right there. All right, the next diagonal is tens. So we have 2 tens, 2 tens, and 4 tens. So here I have 2 tens, EC. Another 2 tens, that's another EC. And then 4 tens, that's an FD. There we go. Now we move on to our hundreds row. We have 300, 600, 100, and 100. So 300 is IFDC, IFDC, and then 600 is, let's see, 600 JGED, and then 100 and 100. So 100 is GFC. So there is our hundreds diagonal. Now we have our thousands diagonal where we have 1,000, 4,000, and 2,000. So 1,000 is JIHGFD. So that is 1,000, then 4,000. We're going to be putting in LKJIHF. And then we have 2,000, so 2,000. KJIHJE. Alright, so now this thing's looking pretty stacked. And then we have one more digit to add in, and that is our 10,000s diagonal. And we have a 2 in there, so 2 10,000s is OLKJF. And then we have to add up all these numbers above each of these bins to reconstruct the final answer. So when we add all of those up, we end up with 28,188. Look at that, we got it right. So now you can see the real power of the location arithmetic and how much time and effort it saves us in the end. If we were just using the promptuary, we would have had to add up all of these individual digits ourselves, up to 4 individual digits at a time. That's no fun. But now that we've used this location arithmetic, all we need to do is add up all... Okay, so yeah, this actually isn't all that nice. Pretty much any numbers that you pick to multiply together, you're going to sign yourself up for even more addition, just reconstructing your number at the end of it, than you would have had if you just, added those digits together. So does that mean that this is kind of a wash? Well, not necessarily. So if we think about what took the most time when we were doing this, a lot of it was converting all of these partial products, these single digits up here, into token piles that we could slide around and mess with. And then converting back from these token piles into our final answer also took some time. But maybe, in some cases, this could be faster if we could do fewer conversions back and forth. So here, instead of doing our multiplication and getting our partial products in decimal, and then converting the partial products into piles, what if we could take the numbers that we were trying to multiply and convert those instead into token piles, and then do the multiplication on token piles instead of just the addition of the partial products? That might end up saving us some time. So let's see how we can do that in the next video. I'll see you then.